Hello, Nadam. How are
Hello,
you
Adi.
today?
I'm doing excellent. How are you?
I'm doing great. We're now recording the sixth episode of our series, and this one's in English compared to the other ones, which were in Hebrew,
Yes.
because we want to expand our global reach and our audience. So we're hoping to get more traction to this episode. And well, I'm Adi, data scientist,
I'm Nadav, software engineer.
and today it's going to be a special episode because our focus, in contrast to the last episode, which we focused on a specific data set, here we're going to work with a specific data set, but our focus is going to be about visualizing distributions.
Let me stop you for a second and give some context to our new viewers that in previous episodes, the ones we did in Hebrew, in general, what we do in these episodes is we take some random publicly available data set and we look at it as if we actually never saw it before, and we try to take some lessons from it, try to explore it with data analysis tools in R. That's what we did so
Thank
far.
you. Great. Thank you for that clarification. Actually, you had two clarifications in one paragraph, right? About the
Correct.
data sets and about R. So we're going to use R, and what we're going to do is to show different methods of visualizing distributions and studying distributions. But before we do that, just a short explanation about why is that important, why is that interesting to study, right? When we start a data science project or something like that, we want to do different things like modeling, visualizing, and basically learning about the data. And one of the important tools on that is understanding the distribution. Also, there are different models which assume things about variables. For example, if we talk about the most known and basic model of linear regression assumes normality of the dependent variable. So even if you didn't understand everything I just said, it's important to understand that in order to qualify for specific models, we have to check different assumptions. And one of them is normal distribution. So that's one of the reasons that distribution of variable is interesting to study. And for additional reasons as well. And I guess that during this episode, we'll get more into that and see different examples. So I'm going to start by sharing my screen here. And I'm also going to zoom in a bit. And let me start by saying that all of the code is going to our GitHub repo, and we'll post a link to that as well in the description of this video. And what I already did was to install a package called palmerpenguins. That's the package we're going to use as our base data. So we are going to work on some data, but the focus is going to be about visualizing distributions. And this data set is basically a data set of penguins. So we've got a small table here of 344 observations with different types of penguin species, which came from different types of islands, with data about their bill length, bill depth, flipper length, right? Their wings, their body mass, the penguin's gender, and the year of their measurement. So we're going to work with that, and I'm not going to focus too much of explaining about this data set any further, but we are going to study the numeric variables here for viewing distributions. So the next step I'm going to do is start a quarter document studying distributions. Adi and Nadav are the authors. And this document is going to accompany us, and we're going to use it to
I will
document
fill in our
everything we're
viewers.
doing.
Quarto is basically like Jupyter Notebook, but for R. And in this case, we're working in Quarto inside R Studio, IDE.
Exactly. Or some would say that Jupyter Notebooks is the same as Quarto. but in Python, right? But no, I'm just kidding.
I guess so, you know.
Yeah,
I do
no,
mostly
Jupyter,
Python nowadays.
yeah, I think that Jupyter notebook, safe to say, it's more common than Quarto. So yeah, I had the typo here with the penguins. Okay. The data comes from the Palmer penguins package. And we're going to load packages. So what we want to do is load the Tidyverse package, which also includes the ggplot2 package for plotting. And we're going to load the Palmer penguins. And that would basically give us the access to the table called penguins. So okay, I got some error message here, but that's not an error, but more warning messages of different conflicts. But that's not of our interest right now, so I'm just going to close that one here. And the first thing I want to do is show you some things about understanding distributions before we visualize them. So there are some base R functions, which helps us study about the distributions of variables. And let's see one of them. Let's see the summary function. So I don't use the summary function that much, but it's very useful actually. Let's say we want to take the penguins, and specifically, let's say we want to work with the body mass variable. That's the mass of the specimen. We can use the summary function, not to be confused with the summarize function we worked with in Tidyverse. Right? We had the summer. Yeah, that's
right. It's not the same.
It's not the same. That's a base R function, and there is also a summarize function, which is very common in Tidyverse syntax. But summary basically gives you some statistics. So it summarizes the body mass, and we can see we get the minimal body mass between the observations. We get the first quartile. So like that's 25% of the data are less than 3,550 grams. We get the median. The median is half, splits the data in half. So half of the penguins are less than 4,050 grams and half of them are above. We get the mean, the average. You can see that the average and the median are not necessarily the same, but in some distributions they are very close to one another, and in other distributions they are very far away. So one of the examples is normal distribution. We'll talk about that later on. Remind me that, and we'll see and understand about the median and mean. We've got the third quartile, and the maximum is, so that's like 75% of the data are under that. And we got the maximal value, and we also got the number of NAs. So out of the 344 observations, 2 have missing values, so no data for body mass for 2 of the penguins in this data. And we can, I think that we can also do a summary on penguins, and it will summarize, I think, all of the variables, right? So you see here, it's not very...
Per column.
Yeah, so we get different columns here. The columns are not very convenient to look at, but if I take this to the console, I think we get a better presentation, right, of this data, because of the row available space in the row.
It takes extra formatting in HTML.
Yeah.
Which is how a Quarto works. Yes,
exactly. So here, when you look at the console, you see that different variables have different types of summary, right? So the numerical continuous variables show us what we've seen before with the body mass. So we've got the B length, the B left, and we've got the minimum, the first quartile, the median, mean, and so on. But for variables with a discrete number of possible values, we've got the number of observations. So for example, in this data, we've got penguins coming from 3 types of islands called Biscoe, Dream, and Turgerson. And we see the number of specimens or number of observations for each island, and the same for species, and and the same for sex.
That's useful.
yeah, useful. So I mean, once you start working with the Tidyverse syntax, I mean, there are, I think, more
How
useful
would you
things
do
to
it in
use, but
Tidyverse?
so mostly, if, for example, if you want to take and get these statistics, you would do penguins, penguins, and then you do summarize, and you can do, let's say, summarize, summarize if is numeric. So you take just the numeric variables and you do something like, I think something like average would be mean. You just do just give the functions, and if you want the standard deviation, for example, which we didn't have here, you'll do something like that. And since you might also
These
want
are
to
function
do
names that you're giving it.
exactly. So and you also want to do NA omit to omit NA values. Otherwise, you just get NAs because of the two missing values we've seen earlier, right? So, or you can also do, I think, something like, give it a function like that, NARM, just like remove NAs, and the tilde sign here, which says I'm going to declare a function. Here it is, and this is just an argument of the function. So this gives us the same thing, and we've got, you see, we've got the bill length, millimeter average here, the bill depth average, and so on, and then later on we've got the SD, and we can add any functions we want, right? We can add the minimum, so that would be minimum.
I think the previous syntax was better because you only had to write it once.
Yeah, I tend to agree on this specific case, that this syntax is much simpler, and gives you kind of an overview. This syntax has different benefits you get out of.
Yeah, if you don't want to ignore the NA unless in specific columns.
I would say that the benefits are not necessarily with the NA, because I can do NA omit here and just drop the NAs there. It would make everything more simpler. But the other benefits are much wider in some sense. Like working in Tidyverse has a lot of working in Tidyverse syntax has a lot of benefits in terms of the flow of the process and how you work with data, like in a much broader and wider sense that we are talking about here.
Yeah.
So that's maybe in the future we'll do some translation of our previous episodes, and I'm guessing that some of our future episodes will be in English as well, so the viewers will be able to see the benefits of working in Tidyverse syntax more thoroughly. Okay, so once we've discussed this, I also want to talk about one other thing, which is called quartiles or quantiles. It's a concept in statistics, right? So what are quantiles? Let's say I want to ask the following question. Like I want to ask for the body mass, I want to ask what is the 80th percentile. I think that's the syntax I'm looking for, or maybe no. Oh, okay, I have to have the NARM here as well. Okay. Right. So earlier when I did the summary of body mass, I told you like this is the body mass that 75% of the penguins are under, or 25% are above, right? So we've got the third quartile or quantile, the 75th percent quantile here, and we've got the 25% quantile here, and the median is 50%. But we can actually get any percent we want using this base hour function called quantile. And we can even do something like this. So we can do something like this. Let's take a sequence between 0 and 1. So this is a series of probabilities jumping by 0.1, like 10% each time. So this is just a vector of the numbers between 0 and 1 jumping in 0.1 every time. And if we take and get this as penguin quantiles, we will see that we get a vector here, which tells us that the 0% is like the minimal observation, the 100% is like the maximum observation when we've got the quantile of each percent here. So we can see how the penguins are distributed. And that's something we're also going to see in ggplot2 syntax about plotting this graph, right? So let me just say that median and quantile are very basic concepts in statistics, basic as the mean is, right? The average, and are in a sense more robust than the average, right? Because the 50%, like you can take one observation to the extreme, like an outlier, but and the mean would change because of that, but the median would probably stay the same because it's the split point of the data. Right? So let's see some methods for visualizing the body mass. Okay, the first method I want to show is called a histogram. And I'm just going to say that body mass is a continuous variable, and we're going to focus today on continuous variables. So these are variables that can take real values, right? And there are different approaches for variables which are discrete, factor variables, okay, factor ordinal. So that's, maybe we'll do an episode on that as well. But today we're going to focus on continuous variables. So the first thing I want to show here is the histogram. So let's plot plotting a histogram. Let's take the penguins, and we're going to use ggplot as our tool here, and we're going to tell it to plot the body mass and adding a geogram of a histogram, a histogram geom. So what did we get here? First of all, we got a warning, right? So the warning says I'm using, oh, that's not a warning, that's information.
Can I ask a question?
Sure.
What is AES?
Oh, so AES is a function of ggplot2, and it tells ggplot2 that I am now going to define an aesthetic mapping. So ggplot2 works in a way which every variable you want to show or base the chart on, you have to map it somewhere, right? So what I'm telling here to ggplot2 is actually map the body mass, and the first argument is x. That's why I didn't have to specify it, but I can also specify that it map the body mass to the x axis, and then I get something like that, right? So the body mass is mapped to the x axis, and the first argument here is just the data. And the plus sign says that now I want you to add a layer called a layer of type geom, like a geometric layer of type histogram. Okay, so that's the syntax of ggplot. And
easy as pie.
Easy as
pie. That's how they say, right?
Maybe that.
now I have to check. Now I have to check this.
You're probably right. Okay, so first of all, ggplot tells me, listen, I'm using 30 bins. I mean, you can change that if you want. You can pick better values if you want. So if for example, I use bins equal 100, I'm going to get 100 columns here instead of 30. So they are much more narrow, and in this array, in a sense, right? The default value here was better for
Probably the
visualizing.
noise is not as useful as
Yeah, exactly right. In if we get too many observations, we get holes because of the fact that we only have 344 observations, and
right.
not every interval
There are
here
missing
has
points.
observations. Yes. So 30 is good, maybe 50 would be better, maybe not, but you see, I'm guessing the default here was better than 50 actually. So that's one thing we got. We also got another warning that now we see just the warning because I specified bins explicitly in this function, but the warning says that ggplot removed 2 rows containing non-finite values. That's the 2 missing values that we had. Okay, so that's what this warning is about. And what this chart tells us, or kind of shows us at a glance, is where our data is concentrated around. So we can see that the mass is between 2,500 and 6,500, the grams, the mass of the penguins. We can see that there is some concentration here around the 3,500, right? Most of the penguins are around this range of maybe 3,000 to 4,000. These are some outliers here. So this histogram is a very quick way to understand what's going on with the data, right?
Just visually, I think I can say it's not a normal distribution, right? You would expect it to be somewhere centered, somewhat more centered.
Yes, you're very right. And this is not a normal distribution. So a normal distribution would be like a bell-shaped. That's the concept in statistics, like a bell-shaped distribution. So you'd get a lot of observations in the middle, which is the mean and median of the normal distribution, and then you get symmetric tails on both ends. So this is not symmetric, and not symmetric around the mean. So this is not a normal distribution. And there are a number of things that can cause that. Like we have different kinds of penguin species here. So that might affect the mass, because different species of birds have different masses. And also the like weight is not necessarily
Could be that
normal.
it's a different distribution.
Right. So let me just save. I'm seeing that I didn't save this file. So visualizing distributions before we forget later on. Okay, so let's try something else. Let's try and split this chart according to species. Oh, and also, maybe not to jump ahead, but it's both species and sex, like the gender of the specimen, because in nature, males tend to weigh more than females, or
not always.
Not a biologist, but yeah, depends on the species, I guess. So let's split that by gender. Okay, so there are different ways to split a chart according to another variable, but I'm going to use facet rep, which is a quick way to do that. And the name of I'm using a tilde here to indicate that I'm going to specify a variable name, and I want this function to split according to sex, and then we get 2 subcharts, right? So we have sex and age. So some penguins, the researchers were not able to discern the type of like the gender of the penguin. And you see we've got the females here and the males here. Now, an interesting thing to note here is that you can see that there are 2 distributions here, right? Even after we split according to female and male, you can see, or kind of see, 2 bell-shaped distributions in this
maybe this is
histogram. Yeah, exactly. That's what I'm thinking as well. So let's try another thing here, and we'll dive into this issue more clearly with another type of chart. Okay, so the next chart type I want to talk about here is called a box plot. Okay, so a box plot is another chart that allows us to look at distributions. I'm just going to take this one here. And now instead of using the geom histogram, I'm going to change that to box plot. I'm going to use the body mass in the y-axis. And in the x-axis, I'm going to use the species. Yes. And I don't need the bins here. Bins is not an argument for box plot. And we can also play a bit with the fill color. So let's use it like that. And I just wanna, another thing I want to do here is kind of just get that away. And yeah, I'm using the pipe here to pipe that. And I just want to filter out the sex and A. So not is an A, sex, just to get that rid of, like, gender and A is not interesting for us. It's a low number of distributions, and we don't want it to mess with our nice charts. So let's check that out and see what we get. Okay, so now you see something which shows us the difference of the different species. And let's talk a bit about how you read this type of chart. So it's called a box plot because it shows boxes, and the box represents the distribution. So you can see a thick line in each box. The thick line here represents the median body mass. So you can see, for example, that the median body mass of Gen 2 penguins, which are males, is approximately 5,500 grams. Okay, that's the thick line you can see around here. Use the annotate, right? So this is the thick line I'm talking about. Okay, and you can see that this box is roughly symmetric. Like the length here and here are roughly the same. So that's an indication, that's some indication that this might be a normal distribution. Like, so when we focus on a specific gender and species, we might get a normal distribution. This is not a statistical test yet, so there are additional ways to test this hypothesis I just said. And very clear, you can see that for some species, that assumption doesn't hold, right? If we look at the chinstrap species right here, you can see that this the median is closer to the end here. So this distribution is not symmetric around the median, not as symmetric as the one we saw with the Gen 2 species. Okay. Another thing to explain here is the two lines. So you can see two lines going on here above and under the box. The box, each box contains 50% of the data points. Okay, so this one here is the first quartile, like 25% of the data is under here. And this is the third quartile. So we got 25% of the data above. And the box shows us the area in which 50% of the data is concentrated.
I have a question.
So, yeah.
If it was, if the data had two peaks on both ends, how would the box look?
So it will still look the same.
It would be lost in the box form.
Yeah, exactly. And if the two peaks are symmetrical, then the box would still look symmetrical. So you won't be able to see if the two peaks are symmetrical, the box would show in the same manner.
Right. So that's why you can't say this is a normal distribution unless you actually dive into the data of that box.
Exactly. So in a few minutes, we're going to see another type of chart called a density. And then you will be able to see the different peaks in the data if there are any. Okay. So And another thing to note here is this point here, right? So the nice thing about box plots is they try, and we got this one here as well. The nice thing about box plots, yes, exactly. So they try to show us outliers in the data. So a box plot has a specific way of calculating outliers. It tries to see if there are any data points which are above or under 1.5 times the interquartile range. So what is that? Very quickly, let's explain what I just said. We've got the interquartile range, also termed as IQR. That's the red line I indicated here in this box.
Where 50% of the data exists.
Exactly. So 50% of the data is within the interquartile range. So we take this size, multiply it by 1.5, and then add it here and under that as well. So if there are any points above the interquartile range times 1.5, then they will appear as outliers. Okay, so that's one way of identifying outliers. It's not the only way, and for some use cases, it's not necessarily the best way.
Yes, it's arbitrary, basically.
Yeah. There is some logic behind that,
Of course.
but yeah, it's not the only way, not necessarily the best way. Okay, so let's continue and look at the well, one very short generalization of the box plot would be a Violin plot. I'm not actually going to delve too deep into that, but it's a nice extension. So it gives you basically a very similar, but instead of showing a box, it shows you the distribution. So Violin plots would always be the same, symmetrical, I mean, in terms of the vertical axis. So there's actually, it's like looking at a mirror, like the two sides would always look the same. And it shows you the distribution. So this type of chart would actually show you if there are two peaks.
Exactly.
Okay. But there's another one which would show that, and that's a density plot. So let's show a density plot. So a density function is also a term from probability theory, which indicates how the data is distributed, right? So when the density function is high, it means that a lot of the data is distributed around these points, and when the density is low. So very, very intuitive, but it's a very deep concept in probability theory. And we're going to shorten that up just to a few lines of code. So let's take the same. The nice thing about ggplot is you can recycle code a lot, and it would work with very minor modifications. So instead of using geom Violin, I'm just going to use geom density here. That's the geometry we're going to use. And instead of body mass being mapped to the y-axis, I'm going to map it to the x-axis. I still want to look at the different genders, but this time I'm going to, instead of using fill, I'm going to use color. These are going to be two lines instead of like, so there's nothing to fill a color with, just to color the line. So the argument here is color. So I'm going to color by sex. I'm going to split
you have
by species.
You provide x twice. Okay.
Yeah, I'm not going to use that. So what we get here are three subplots. This time I'm separating them, like each subplot relates to a specific species, and you can see the females and males on that plot. So it allows us to see the distribution of males versus females within each species. And you can also see that this looks more like a normal distribution. So you can actually see that the Gentoo looks like normal distributions, right? and the chin strap not so much because of that little hump you got there. And the elderly species maybe also normal. That's something that, like, if we wouldn't have split that by color, you would actually see that there are two modes for the distribution. You see here? So this is one
it does
of
not
the,
separate.
yeah. So I intentionally left that out, left the color equals sex. I left that out to show you what would be a good indication that a split according to a specific variable is something that might turn a non-normal distribution to a normal distribution because it's made of two normal distributions intertwined, right? So a density plot is a nice way to kind of look at that. Okay. So next up, we want to look at an empirical cumulative distribution. So what is an empirical cumulative distribution? That's a more, I would say, more complex plot to understand and read. But you can sometimes get a lot of insights from that. So let's see that, if you're used to looking at that.
Can you write what the ECDF means there?
Yeah, so thank you. Let's do that. ECDF's empirical cumulative distribution functions. So to those of us which learn math or probability, an ECDF is the integral of the density. Okay, so that's like looking at the area under the curve here of the density function, integrating this function. And that shows us that connects us back to what we've seen here in the quantiles. So that's the function we're going to plot now, right? We're going to plot the function in which the x-axis is going to be the mass and the y-axis is going to be the probability.
Okay.
So this function would always go from 0 to 1 on the y-axis and would cover the range of the variable we're studying, in this case, the body mass. So let's see how we do that. We're going to use body mass and map it to x. And we can also, let's do color equals species. So that would give us three lines within one chart. And I'm not going, like, we got the concept with the gender, like we can also split that by gender if you want, or vice versa with the gender and species. So I'm not going to do that right now. And now, instead of adding a geometry, I'm just using a stat ECDF. So the geometry here is actually a line, and the syntax here requires us to add stat ECDF. And I just want to see here, because I've got this small arrow, but I don't see a syntax arrow, so I don't understand why is that exactly.
Try to run it, maybe you'll get an error.
Yeah, I don't see an error here. Yeah, okay. So first of all, we get something which looks like steps. Why is that? Because we only have a discrete number of possible values. We have a small sample of penguins, like 344, and they're split across the different species. So we get the steps here. And what this chart shows us is, or how to read it, is, for example, if we look at the 5,000 mark here, we see that for the Gen 2, that's the green color chart here, green color line, the 5,000 accumulates to about 50% of the data. So that's exactly what we saw earlier, right? But that when we computed the median for or when we saw the box plot, but the box plot only gives us the 25%, the 50%, and the 75%.
Right.
The thick line in the middle and the two lines which border the box. But here we get a higher resolution. So if, for example, you want to see like 12% of the data, you just take it somewhere here, and you see that 12% of the data in Gen 2 is around 4,500. Right.
Right.
And also interesting, you see that there are like an interesting question would be the body mass is a continuous variable, right? But when scientists measure the body mass, if you get 4,995, what would you say? You'd say
4,995.
Yeah, but you see that there's a jump here.
It could be that they just didn't have the sample, or that sample went off because they didn't know which gender it was NA and filtered out.
No, like NAs are completely filtered out here on this chart.
Right.
But the story here with this jump is rounding.
It rounds.
So it's not R doing the rounding.
It's in the
scientists
data.
Measuring. So you got a lot of observations with exactly 5,000 grams of body mass because scientists measure and then they round. So if they measured 4,995, they might round it to 5,000.
Right.
This is why you get this jump here. You see? So you see jumps like 5,500. You also see this jump right here. Right. So it might be due to the accuracy of the measurement device, but there's no reason for a large number of penguins to be exactly at 5,000. The reason is that the measuring device
the human factor
limited, or the human factor exactly rounds because it's easier, and it might be completely fine. Like for understanding the species, it's not important if it's 5 grams under or above or exactly, right?
Yeah, we don't know if the resolution is even matters, if it's sufficient or not.
Yeah, it's probably sufficient for most things here. So how many did we do? I promised 5 types of charts, right? So we had this histogram here.
No, but you modified
the
several.
Box plot. Yeah. So
the violin was a box before, right?
Yeah, so let's get that back.
No, you should copy it so we have both.
Yeah.
I actually like the violin. I didn't know about it.
Yeah. So they're very similar. So I include them under the same type of chart, even though they're different. And that's 1, 2, 3, 4. Let's get that back with the gender. That's the one we had here. And the ECDF. And I just want to show another thing, which is the scatter plot. Okay, so the scatter plot is something that you can do here because we don't have a lot of data. Scatter plot is just going to scatter points on different axes. And I really like this example. I show this example a lot to my students when I teach Introduction to Statistics, because it shows you how you can learn a lot from using plots and charts. And it can show you that some things can even be deceiving if you don't put the effort in to understand how to visualize them or to learn them, right? So I'm going to switch into 2 other variables. And instead of using the penguin mass, I'm going to use the bill length and bill depth of the penguins, right? So that's like the length and depth of the beak of the penguin. Penguins. And I'm going to start with just plotting the bill length and bill depth like this with geom point, and that would give us a scatter plot. So let's see what we got here. Now, looking at this chart, if I would have asked you what is the relationship between build depth and build length, or even if there is a relationship between the two. I'm not sure that you would be able to identify any relationship, or maybe some kind of a decreasing trend, because you see the points coming down around here, right? I mean, that would be a reasonable first guess with this chart.
Fair enough.
Fair enough. But now I'm going to surprise you and tell you that the relationship is an increasing one. And the reason you're not seeing that is because we're not visualizing it with the right aesthetics, or not enough aesthetics. Like, we should add something here. We should add
maybe color, or
yeah, we should add a color. But the question is what to use for coloring. Like, what variable is going to be mapped to the color of the points?
weight, maybe.
So weight is something that we would find it hard to map as it is, because it's a continuous variable. So there is no, like, that would give us a scale of colors.
If we wanted, we could have broken it, I guess, into quartiles or something.
Yeah,
okay.
That's exactly right. But I already know the answer, because, as I said, that's an example that I show a lot. That's an example that I show a lot. So we're going to use the species, and we're going to see the relationship of
copy the plot. Don't overwrite it.
Okay. So this is a misleading story. Let's comment it out here. And this gives us a much more insightful chart. Right. So let's see. And we'll add the color here. And now you see something completely different. You see that as the build length increases, the build depth increases as well. And the reason we didn't see that before is because we didn't split it by species. And you can also see that the trends are different. Like, we got the trend here with the Adelie is a steeper trend than what we see with the Gentoo, right? The slope of the relationship. You can even add something called stat smooth, which will add a linear model. Oops, jumped here, which will add a linear model for each of the groups. So that gives us a linear model, the linear relationship, or the linear regression between the build depth and the build length. So you can see, actually, they're not that steeper. The slope is actually very similar. They're almost parallel to one another. Yeah. So this is another way of showing the distribution of variables, and, to be exact, the relationship between different variables. So it's not the distribution of one of them, but of two, and not exactly the distribution, but more the relationship between them. And this is important, because things like that can lead us towards modeling the data. For example, if you would have wanted to create a classifier, a classifying model, which gets the build length and build depth as data, and outputs the reasonable or the probable type of penguin you're measuring, you now know that build length and build depth should be within that model, because they treat one another differently with different types of species. So it's something that you can probably create a model around. And that's an insight that you could have gotten from this one as well. Like this earlier chart, in which we talked about, like the box plot chart, in which we talked about body mass, can tell you that body mass is also a variable that a classifier would most likely use efficiently. Because, for example, if we talk
At
about
least for
males,
Gen 2, I would say.
yeah, for Gen 2, exactly. So body mass is something that can separate very good between Gen 2 versus the other two species.
Correct.
So I think that that's what I was aiming at the beginning of this session when I said that understanding the distribution is important and visualizing the distribution is important because it can lead us to better model building, model fitting, and to understanding what aspects of our data are important in our research and in our work towards improving our understanding, insights, models, and so on.
Very nice.
So, yeah, I think that was
Insightful.
fun. Yeah.
It was.
Yeah.
You want to do a recap?
Yeah, sure. Go at it.
So we started by looking at the Quarto in RStudio, and we loaded the penguins database, which apparently is a package you can download for R, like a demo package. And we looked at the basic R functions like summary, not to be confused with Tidyverse summarize. And then we looked at how we do the same with summarize and a bit more. And then we looked at quantiles. And then we started looking at how we can visualize the data by histograms and by violin and box plots and the rest of them. Density plot, correct, and plot in ECDFs.
Exactly.
And we looked at a scatter plot and learned how it can be more insightful if you know how to separate the data correctly, if you know how to visualize it by which parameter.
Exactly.
Yes.
Well, yeah, thank you very much for that recap. And as always, let us know what you thought about this episode in the comments below. Subscribe to our channel. We promise to do more episodes in English for
Yes.
our
International
audience. Yes. See you in the next one.
See you.
Have a great day.